Okay. So that's what I have planned for today. Okay, let's see if we manage. But so basically, I just wanted now that you have done a few exercises with, Snow White, dry gas, and also you did this network with, it was Gulfax. So I think from there we can gather some general conclusions on that. Okay. Then we're going to talk about ESP, electric submersible pump. We mainly basically cover it quite okay, but it's just some orientation for solving that problem. There are a few things that you maybe haven't been exposed to before. And finally, we start with a new topic. I told you that we started with how the machine looks like when you have single phase pumping, when you have liquid. And then we are going to look at compression, because compression, there is something very special. Here in pumping, we were just looking at the pressure. Okay, the energy basically is simply the increase in pressure. But when you go on compression, you have to look both at pressure and temperature. You cannot look anymore only at pressure. And then multi-phase boosting is something in between. Okay, so that we are not going to cover here, but it's just to give you a taste that when you have both extremes, what you have to be careful about, and when you have something in between, you also, so you get some idea. Yeah. So let's see what kind of methods. So what can we do to prolong production? And remember now, we are in all of this is kind of, I call it the field performance part. Okay, our main task is to predict how the field will produce with time and how we can change that performance. That's our full objective here. That later goes in the planning phase for development studies, that goes in the operational phase to design how can I improve the production of the field, but that's the main focus here. Typically, this part on pumping and compression and emulsion, I left it for the end, okay? But I thought was kind of nice to have a full block and then to continue with the other topics, okay? So, okay. Methods to prolong plateau production. What do we have here? What can we do based on what you have observed?
Number of wells.
Yeah, we can simply increase the number of wells, right? Okay, and if you see increasing the number of wells reduces the rate per well, therefore you have more available pressure, or put in another way, gives you also more potential. Okay, so you can have more potential and then the decline will happen later. What else can we do here? No, that usually if I'm fixed by a contract, okay? Usually if you are on a gas field, you are obliged by a contract to deliver for a certain amount of years. And that happens if for some reason your decline happens too soon, okay? Or you enter into a new contract, you just want to extend it. That's also possible to do it, okay? And for an oil field, simply you don't want to enter into decline, okay? Remember, decline tells you I'm recovering less oil or I'm recovering oil later in the life of the field. Okay, if I prolong plateau, I recover earlier, then the revenue is higher because of this discount, okay, that we have in our heads all the time. This discount factor, if I produce it in 3 years from now, is not the same that if I produce it today. How is that factor, by the way? If I produce today, let's say 10 barrels, and in 3 years, how is this discount factor? How big it is? If I say produce 3, let's say 1 barrel, right? And the price now is, today? 70? Yeah? Okay, that's what we get today, okay? US dollars per barrel, we get $70. But if we get it in 3 years from now, how much is that? What is the discount factor? 1 over 1 plus 0.0, what number did we use? 7? Right? To the power of 3. Okay, so how much is that? Is that factor? Okay, 0.81. Yeah. Well, the inverse of that, I guess.
Yeah, fine.
Okay, 0.81. Okay, that means that after already 3 years, I'm going to get, 1 times 70. And that number is going to simply become bigger. Let's say after 10 years, how much that will be? Okay, 0.5, half of the value that if I produce it today. Okay, so this something, remember, when you're developing and producing a field, something you have over your head. Okay, you produce earlier is better. Maybe not from the reservoir, but for the pocket is, okay? Okay, 1 times 70 divided by, yeah, so what else can we can increase the number of wells, we can somehow increase the productivity, right, the available pressure. How do we do that? How do we make the available pressure bigger? We can use boosting, but that's actually adding energy to the system. Okay, I'm going to put it here, adding energy to the system. Okay, and I add energy basically by using boosting. Okay, that here I'm saying compression, pumping, and I can also do using artificial lift. Okay, that for example ESP. What else can I do? I can try to change. Remember, we have these resistance coefficients in the case of the dry gas in every place of the system. We have one equation for IPR, we have one equation for TPR. So if these coefficients, we somehow make it bigger, the available pressure simply will be bigger, right? So how do we make the C of the reservoir bigger? The productivity of the reservoir. We can do fracking, we can do acidizing, we can do well stimulation. Okay, so that's making C, okay, bigger. So that will be fracturing. I can do well stimulation. Okay. How can I change on the tubing? What can I put on the tubing to change?
The time.
I can maybe make the tubing bigger, okay, but that's also, so here I'm going to put simply in red, this usually is expensive, okay. This is also expensive, but can serve also a larger amount of wells. Well stimulation usually is in the lower end, can be expensive, but not as much as drilling a new well or then changing tubing, making, that is basically making CT bigger, right? And that is, one example will be to increase the tubing size, and that happens sometimes. Okay, that also is expensive. Or it might be that you have some accumulation of some solids on that tubing. Okay, and with time simply the pipe becomes smaller and smaller, the cross section. So you can clean the pipe. You can somehow remove the, I would say, the deposition, the remove solid deposition in the tubing. The same thing could happen in the reservoir. You have some deposition, precipitation of scale, for example. You can inject some chemical just to try to make that out and kind of make the pore space as it was originally. Okay, what else can we change?
Make a bigger pipeline.
Make a bigger pipeline. Okay, and that's a very good alternative if we have just a very short or relatively short pipe. If we have this in Snow White, this 140 kilometers pipe, you remember how was the cost of this pipe? I think it was $500 million, I think, or yeah, we can check. Okay, so it's not so recommended for. Maybe I have it here. Yeah, I think it was in the exercise. Okay, so it's a big investment, and the pipeline, $500 million. Okay, so it's a big expense. If you say, well, I want to change that now to a bigger pipe, maybe you're going to get fired, or I don't know. Okay, but we can put it here, making C of the flow line bigger. Okay, and that is simply by saying increase the size, increase the pipe size. Okay, which can be a cheap solution, or it can be a expensive solution depending on the size, the length of the pipe.
Cleaning? Cleaning, digging, or?
You, on that case, CFL, we are now assuming dry gas, right? So there is nothing else there. But if we are going with different phases, okay, we can have also, for example, let's say we have gas with some liquid, okay, and the liquid, we have some accumulation of liquid at the bottom of the pipe. The effect that that's going to have is basically like an obstruction, okay? Simply like if you have something deposit, is a reduction in the cross-section area. So you can also do pigging to remove those liquids and simply like increase the C flow line, okay? Perform pigging, okay? But be careful. If we have, remember our simple system of, we always have to see what has the most important effect. Okay, remember this system. Okay, let's make the equilibrium now here at the wellhead. Okay, we have here a flow line and we have a well. How P wellhead? Okay, versus Q. How does it look like? Something like that. Okay, and P of the flow line might look something like that. Okay, so be careful. Changing the flow line, okay, will give you, yes, it will give you higher plateau, it will give you longer plateau. Okay, but if this curve is already very, very flat, okay, and you are going to propose to use a bigger pipe, really the increase in rate is not going to be worth the investment. Okay, and the same thing applies with tubing and with reservoir, with all kind of things. So you always have to see on that chart, then make the estimation how much are you going to gain, okay, and then see what is the most relevant for your system. Okay, and you can see some systems, they call it, that system is tubing restricted, that tubing is formation restricted, that system is pipeline restricted. That is the most important component that is affecting the performance of your system. Okay, so you have always to look which one is the most critical. It can be that all of them are critical. Okay, what else can we do here?
Decrease pressure in the separator.
Decrease pressure in the separator. We don't like it too much. Okay, process engineers don't like it at all. Okay, but remember, we have two pressure bounds. Okay, one, we cannot control much. We are draining and that's going down. Okay, well, maybe we can control a bit. Okay, but the other is the separator, and if we lower that, we are going to get more production. So decrease P separator. Okay, but here we have to be careful with angry, okay, process engineer, and we have to be, okay, careful with processing requirements. Okay, then we can also try to slow down the decline in reservoir pressure, right? That's the other node that we have. So how do we do that?
Water injection, pressure support.
Yeah, water injection, gas, maybe we don't do it, but would we try, let's use a pressure support mechanism, okay? If we can, okay? If we have a if we have a oil, we can just simply inject gas or water. If we get gas, it's slightly more complicated, but we want to simply support reservoir pressure, so the decline won't be so abrupt. What else is missing on the list? Yep.
Can you connect the high pressure reservoir with a, for example, low pressure water reservoir and use the high pressure reservoir as boosting?
As a what?
As boosting. It's some master students are writing thesis on connecting a high pressure reservoir to a low pressure reservoir and use it as a booster.
Yeah, you can use the energy. Remember, here, when we are operating at plateau, we have here a pressure drop, okay, in this choke. So basically, that pressure drop, you have to see it as a waste of energy and burning energy in that localized component, okay? So if I can use that energy for anything else, for example, I have a gas reservoir, I can use high pressure gas to make gas lift, okay, in some other field. So I can try to make some but but that depends if I have exactly two fields that are very different from each other, very close, okay, and that's usually not the case, okay. But you need to have, like you said, a source of high pressure, maybe gas someplace, and you need to have another reservoir which is low pressure, low energy, and then find a way how to convert the energy from one to the other. But it's not so often done. What else? There were many of you that came with a nice solution last class, okay? What was it? When you wanted to keep production, okay, keep plateau. You had one that was choked, one that was not choked, right? And you say, well, why don't we increase the rate from the one that is choked, okay? So that is basically, so you want to redistribute production between the wells, okay? Redistribution of production. Okay, and that is usually a very good way to do it. Usually we have some producers that are very good, that have that are choked, and those that reach the end of those that they start declining. So you can simply increase the production from the good producers, the one that are choked, and then keep the other one, reduce it. Okay, and with that you compensate among wells. Okay, but here you have to be careful with and there are two things, okay? First, maximum allowable drawdown. Okay, that PR minus PWF, you might have a limit due to sand production, due to all kind of issues, wellbore stability, sand collapse, okay? And you have maybe a limit on the rate, okay, Q maximum. And you might have coning, you might have water coning, gas coning, all kind of things. So be careful if you're doing that. Be careful not to go above that limit. Okay, and I think that more or less covers. There might be some other things we are forgetting, okay, but that basically covers kind of the overview of the method. Okay, making available pressure bigger, making required pressure lower, adding energy to the system. Okay, and simply using the same system but redistribute. You detect which component in the system has reached its potential, and you try that. You keep it on potential, but then you increase from the others that haven't reached yet the potential. Okay. Now let's go to some clarifications for problem 2 of exercise set 3. Okay. And the field we are going to look at here is, let me go to the exercise, is Peregrino. Okay, is this field? I don't know if it will come. Okay, it's offshore. It's very poor. Okay. that is offshore Brazil. It's operated by, actually it's very close to Rio de Janeiro, and it's operated by Equinor, by Statoil. So you're going to have to make calculations on that field. And the way that field is produced is you have, let me see if I think there is another figure here. Okay, so it's produced with, let me paste the reservoir, I think. And the reservoir here. So it's produced from two platforms where the wells are in those platforms. You have a very, I think, one stage separation here on those platforms. And then all fluids are sent to an FPSO for central processing. Okay, so basically you have the producers are, and these are wells that they go all the way, the wellhead goes, the Christmas tree is located on the platform. Okay, we're going to see now why, but these wells basically they have these electric submersible pumps inside. So these pumps, they have a life maybe of 2 years, between 6 months and 2 years. So you have to go and enter into the well and change the pump. Okay, and because of that, if they make it subsea, it will be very expensive to do that every 6 months or 2 years. So they simply make platform, and so they can access whenever they want. And you see here you have the tower where you can access whenever you want the tubing, the well, change the pump. Okay, and this should be actually, let me see if I make it bigger. Okay, so you have a set of wells, you have injectors and producers on each side. Okay, and what is curious about that field, or why we are using it for our example, is that it has a very low GOR. Okay, and it's because of the water injection has an underlying aquifer which gives support, but you're also injecting all the water that you produce. Okay, all the water that you produce comes here, is processed, and then it goes back to be re-injected. Okay, so at the end the field will produce quite a lot of water. So if you see, you go to, I think we have the profile of the field in this Excel sheet. If you go towards the end, you see what was, and that was produced by Reservoir Simulator. Okay, Reservoir Simulator, you get the profile of oil, which you have a peak and then starts to go down. Water, initially you have no water, then you have breakthrough and you start producing water. And reservoir pressure, the injection you have is not enough to maintain the pressure, so simply will start to decline slowly. Okay, we assume here a kind of a straight line decline. Okay, so you have here to look at what was, so taking these rates. Okay, you are now going to play the production team. You're in this field development concept. They say the reservoir guys, they came with these profiles. This is the best to drain the reservoir. And now you have to verify with the pumps that you have, okay, with the ESPs that you have, that the ESPs are given here. Okay, here we have a map, how it behaves. Okay, so you have to verify. I think I gave 4 dates. Okay, 1.7, 7.5 years, 14 and 25, to verify if you will be able to produce the rates with those pumps. Okay, that's your main objective. And this is keeping things disconnected. Okay, they have done on the other side the reservoir simulation, the decline, and now we are getting the results and we are trying to verify, is this rate actually feasible, if I can produce these rates. Yeah, so but there are a few complexities. Okay, like if you see here, so let's go first to the yeah. So one thing is that the amounts of oil and water are changing with time. Okay, and that's not only affecting, you know, what comes from the IPR, what comes from the formation, but it actually also affects every system downstream. Okay, in our case we simply have the tubing. In our case we're going to say simply that the wells are, I think I have a drawing, sketch of the wells. Okay, that's how they look like. We are not going to go too much in detail into completion. Okay, but basically what you have to see here is that you have a horizontal section, then you produce suction into a pump, and then you have the annulus is actually closed. Okay, so everything has to go through the pump. That means the pump has to get only single phase liquid, and the GOR and the bubble point pressure is so low that basically we are going to assume that everything behaves, that you have liquid all the way going up. Okay, but the sketch, okay, you have the horizontal section, producing section. You cannot put the pump usually there. The pump cannot run horizontally. They have to run relatively vertical. So you have to take it to the vertical section. Here you have the suction. The pump is this blue thing here, and then it's pumped up. So if we make a simple sketch of our system, okay, you have the annulus basically is closed. I'm not producing anything, and simply I'm flowing from the formation to the suction of the pump. Okay, that's my ESP. And then here we are going to assume, because all of them are on the platform, okay, and we are going to say they are very close to the separator. So we're going to neglect any flow line, anything. We simply are going to say all wells have, simply they have a constant pressure, okay, and P separator. Okay, so that's going to be our basis for calculation. Okay, now how do we calculate what you're going to need, right? We're going to make the same thing, available versus required. Okay, so where do I put my equilibrium point in this system? Remember, we always have to think before we make calculations, where are we making our equilibrium? And then try to see graphically how it's going to look like. And then we go and use the equations, okay? What equilibrium point do I use?
ESP.
Okay, I'm going simply to make it here, okay? That's going to be, it's not a point, but it's actually an area. The ESP might have a few 100 meters, okay, of length, because you have many stages, you have the motor, you have, but actually we're going to make it here. We're going to say that PWF, so we're going to say the P suction of the pump, okay, that's how we call it, is the P inlet to the pump, is very close to PWF. So we can say effectively that P, I don't know if that's how we have done it here. Let me check. No, actually we have some distance, okay? So we have to have this H1. So we have P suction is a P inlet to the pump. So I have to go, remember, from formation to bottom hole, I have to go PR to PWF. I use that my IPR equation that you already suspect. Okay, we have one equation for liquid, which is Q of the liquid. Here we use for both phases. Okay, we are using Q liquid means liquid rate of this Q liquid is rate of oil plus rate of water. Will be a J times PR minus PWF. Okay, now we have to move all the way to the suction of the pump. Okay, now we go PWF to P suction. Okay. What equation do we use there? Yeah, you use the tubing, but you cannot use the dry gas tubing equation we have used, right? That's for compressible fluids. So what do we use? If you remember from your kindergarten fluid dynamics course. Okay, we can use that equation, the Bernoulli equation. We say 0.1 and then we go to a 0.2. What they say is that H1 will be equal to H2, the energy. You have this head, okay? And the energy is basically P1 divided by rho 1 G plus B1 over 2G plus what other kind of energy do we have? Z1 will be equal to P2. Yeah, the density is the same, so you remember that equation, right? Okay. And if we have losses, how do we account for losses in this equation?
Add a friction term.
We said if we flow from 1 to 2, we add a friction term. So we say the energy on 1 will be what you have in 2 plus what you have lost, okay? HF, which is like a friction thing. And this friction,
What's ZG?
Z is the elevation.
So it'd be
No, it's
Z1.
2G.
2G.
2G. Okay. HF, the expression we use typically is FL over diameter of the pipe times B squared over 2G. Okay, so that's the equation we are going to use. We say that's for single phase liquid, single phase, and also incompressible fluid. Okay, and we can put it in terms of what actually we are calculating is pressure with rate, right? So we can say, let's say if we want to use here, I can create an equation called line, okay, or tubing P1. Okay, P1, I clear P1, then I'm going to make the approximation that B2 is very similar to B1. Therefore, those terms, they cancel each other. So I get Z2 minus Z1 times density plus FL times, this goes away, okay. Remember, this F is a friction factor, is actually the Moody friction factor. Okay, what you get from a chart, from this chart where you have the laminar regime, you have to distinguish if you're in the laminar regime, which is a straight line with Reynolds number, or then you have this behavior which depends on the roughness. Okay. And be careful, some equations they use the fanning friction factor, and you have to be careful. Okay, L is simply the length of the pipe. But our equations are always one pressure, inlet or outlet, as a function of rate and the other pressure. Okay, so where do we have rate here? V, the velocity, we can say is the rate divided by the area, the cross-section area. Okay, so we have Q pi times 4. Okay, and we can simply substitute that in this equation. So we end up with P1 here we had 8 to the 5. Okay, we end up with that equation. So there you have, you can clear out, of course I'm forgetting P2, I don't know why. Okay, I can clear out P2, can calculate P at the outlet. That's the one we need to use here. We're going to calculate P at the suction of the pump going from the bottom hole pressure. Okay, from the bottom of the well. Or we can do the opposite. Okay, we can use, if we have P2, then we can calculate P1. Okay, now be aware here of something. This Q is the local rate. That means the local rate at pressure and temperature. Okay, is not the same as the Q at standard conditions. Okay, Q oil, Q water, or Q liquid. Is not the same. Okay, remember we have, like in the case of oil, okay, we have pure oil circulating in the pipe at pressure and temperature. Okay, then we take it to standard conditions through it. It can be through a surface process. Okay, usually have a series of separators. This P can be simply flashing to standard conditions, a constant composition expansion, or I can use simply the real process that I have on my plant. Okay, usually it's a set of separators. And I'm going to get finally here, I typically get oil, but I'm also going to get some gas. Even though this field has very little gas, I'm going to get some gas out. So that will be volume of oil that I have here, that is the local that I have at those pressure and temperature. And here I have V of oil at standard conditions. And the V of gas at standard conditions. Okay, so petroleum engineers, they create this factor called VO, that is simply VO, the volume of oil at local conditions, PT, divided by VO at standard conditions. Okay, which is simply a factor that takes into account first the compressibility. If you had no gas, simply it's due to the compressibility. Okay, if you are at high pressure, then the volume becomes smaller. If you are at low pressure, then it expands a little bit. Okay, but here you have the effect of gas. And this VO can be very significant, can be 1.8 maybe to 2 for volatile oils. Okay, and it can be around 1 for dead oils. Okay, or for black, kind of black oil. That's the approximation we're going to use here, okay, in this exercise. For this exercise only, okay, this VO will be equal to 1, and also the V of water. You can do the same with water. It's going to be equal to 1. For every condition, for all pressure and temperature. Therefore, the Q of oil local will be the Q of oil at standard conditions. The Q of water local will be Q of water at standard conditions. And the Q of the liquid will be the Q of the liquid at standard conditions. An assumption, okay, just to make your life easy. If that's not the case, what do we do with that equation? Can we still use this equation? We can, but we have to subdivide in segments, okay? Where we think that the volume is constant and the density is constant, and then we proceed, okay? We have to discretize. But we want to take that, you know, not that complexity out. So that's the equation you're going to use for the flow, both, okay? Let's call this the pipe equation for single phase flow. Okay. So to go from PWF to P suction, we have to use that equation. Let's call it equation, I don't know what, 1. Use equation 1 with here you have to use P1 will be PWF, P2 will be P suction, that's what you want to calculate, and the Q will be the Q of the liquid, because you have to take into account all the liquid that comes in there. Okay? Now, what happens with you know, we need the density, okay, and we also need the viscosity. What do we need the viscosity for? The Reynolds number, right? We need the viscosity for the Reynolds number. So for the density, we're going to use the density of the mixture. That will be is something typically used in multi-phase flow. When we have a mixture of two fluids, I can create a density of the mixture based on the density of the oil times the volume fraction of the oil plus density of the water times the volume fraction of the water, where the volume fraction is based on this local volume rate, okay, is QO divided by QO plus Q water, and alpha water is Q water QO plus Q water. Okay, here we're making the assumption they are the same, the local and the standard, but be careful, this definition is on the local, using the local flow rates, okay, volume rates. Or I can express everything in terms of W1 minus this W plus times that. Okay? Because the sum of both, I have only oil and water, so the sum of both are going to give you, it should give you 1. Okay? And the idea is that basically the thinking behind, if you have a column, okay, filled with simply with one fluid, oil, you have some hydrostatic, you know, pressure difference, okay, between top and bottom. Now if I fill half and half, and they have to be in volume basis, now I'm going to have a different hydrostatic pressure, okay. So this definition is honoring that, okay. It's honoring that if I have now two fluids, let's say now I have on my tubing, it's honoring basically the pressure, the hydrostatic pressure, even though they are not segregated, okay, they are mixed, but the effective density is using this expression, okay. What is the definition of water cut? Of a field? It's simply Q water, but water where? At the surface, okay? So water cut is Q water divided by Q oil plus Q water at the surface, okay? So be careful, it's not the same as the volume fraction. For our exercise, water cut will be the same as alpha W, okay, the water fraction, but only because we are making this assumption that the volume that's called the oil volume factor is 1, okay, and the water volume fraction is 1. If not, they are not going to be the same, okay. So the other comment is that we need viscosity for the Reynolds number. And the Reynolds number we need for the friction factor. Okay? Let me just write it here. And some people, they propose simply use the same equation, okay? Some people use simply viscosity of the mixture will be the viscosity of the oil 1 minus alpha water plus the viscosity of the water times alpha water. But there is something, behavior which occurs in the field and in real crudes, that is called emulsion, that you have to be aware, and that's what we are going to use in this exercise. We are going to use it also to introduce the concept of emulsion. So if you're recording the delta P, you have a pipe, okay, horizontal pipe, and you're circulating certain rate through the pipe. Okay, you're circulating with certain velocity. So if you use pure oil, okay, that will be alpha water. So if it's 0, that is pure oil. And if it's water, you have is 1, pure water. Okay. So if you start to change, initially here you get the loss for pure oil, okay, and here you get the loss of pure water, which will be lower. Okay? But if you start to change in a continuous way from 0 to 1, you see that the delta P has a very strange behavior, has something to do with that. Okay? Has a peak. And this peak we call the inversion point. Yeah, we have to take a break, but let me just finish this explanation, okay? So the thing that happens is that when you have pure oil and you start adding water, you see that you have, it's basically a dispersion oil, we make it with green, right? A dispersion of water in oil. Okay? And on the other hand, if you have water and you start adding oil, you have the opposite. You have water, a dispersion of oil in water. Okay? But the thing is that you have this transition point where it flips from one type of dispersion to the other. Automatically it flips. But that comes with a very high pressure drop. Okay? So why is that important for the performance of a field? Okay? Because typically, what is happening when we start, like this case, okay, this peregrino, this field, okay, what is happening with the water with time? Okay, simply increasing. Therefore, we are moving from this alpha all the way to here. And if we at any point find that point, that point can be very high, okay, can be maybe 10 times from 3 to, okay, from 3 maybe to 10, 20 times the value of delta P alpha water 0 oil. You're in trouble, okay, because now you will have a lot of pressure drop, and now your equilibrium happens at a very low rate, and then you are not able to produce anymore. Okay? Yeah, let me just, before we go to a break, just to show you how it looks like. Okay, and an emulsion we have made here was a student. She was visiting from China. She made some nice experiments. Her name was Chensi. Okay, and I have it here, I think, someplace. Okay, that's how we have it. The two fluids are mixed, are separated. Okay, then we put it on a blender. It's like making mayonnaise. Okay, you put it on a blender, and at the end you end up with this thing, and this is very difficult to flow. These two are fine to flow separately. That mixture is very difficult to flow. Okay, so we have in our production system, we have all of this shear. Okay, the blending is like a shear effect. We have shear when we go from the formation to the bottom of the well, when we go through a pump, when we go through a choke, we have a lot of shear, okay? So that shear causes the dispersion to become like an emulsion, okay? Like what we have here. So let's take a break now. Let's say, 15 minutes. So we come back, 22, something like that. And we see how we are going to model that emulsion, okay? So the way we deal with this emulsion problem, okay, the people typically calculate, they say, well, we are going to use the same equation as for, for a mixture, if it was just a single phase fluid, but we are going to use back calculate the viscosity of the mixture. That will give them the same pressure drop. Okay? And basically it gives you the curve, a very similar curve like that. Sorry, water. Okay, they simply back calculate from that pressure drop a curve for the viscosity, or they measure the viscosity in a beaker. They mix it and then they measure with a viscosimeter. They measure the viscosity. Okay, the inversion point usually happens, something depends very much on the crude, but happens between 30 and 60% of water. Okay. So the way we're going to model this, there are different equations, okay, but we're going to use the Richardson equation. Okay, the Richardson said that the viscosity of the mixture for the oil continuous, for this region, oil continuous will be the viscosity of oil times an exponential of a constant that we have it times the fraction of the dispersed phase. In that case is water. Okay. And for water continuous, then it's the viscosity of the mixture is viscosity of the water times E CO 1 minus alpha water. C water, sorry, not CO. Okay. So that's the approach we're going to use. So if you punch Alt F11 on your problem 2, you will see you have different sections, but I think it's in the flow equation. That's not that problem, sorry. It's problem 2. Okay, emulsion, you have that equation, okay, that uses is one equation taking both. If you are above, we call that the inversion point or the cutoff point, okay. If you are above that, then you're going to use the expression with water, and if you are below that, you're going to use the expression with oil. Okay, and here you have your constants, exponent water and exponent oil. Okay. For our case, the emulsion point, the inversion point is 60%. Okay, viscosity of the oil is very viscous, is 100 centipoise, and the viscosity of the water is simply 1. Here you have the density. I think also we have an equation to calculate the average density. Okay, this one, average property. So let me copy, just make a screenshot of that so you have it. Okay, that's this Richardson equation. That's what you're going to use to calculate viscosity. Typically I have to inject, besides being careful, okay, with that point, when I'm going to be around that point, we have to be careful. We can also inject demulsifier. Okay, just to try to make it that the dispersion won't be so stable. You are injecting demulsifier. And in that case, in this field, the way it is done, they inject it at the suction of the pump. So they have to make a hole on the tubing hanger, and they have to send a line with some chemicals, demulsifier, all the way to the suction of the pump. Okay. So that's the equation for, and we also have the equation for the average properties, which was here, I think, someplace. Okay, and then the equation for this Bernoulli equation with the losses, I think they're also here on the same. You have P in, okay, if you have P out, you have to give the angle to calculate the elevation. You have to give the viscosity, density, the length, and the roughness. And with that, you use a function called friction factor, okay? And friction factor simply verifies if, actually here it needs one more, okay? It's not correct. You should have one for laminar flow and one for turbulent flow. That's only for laminar flow. Okay, but it's using that expression with the calculate the Reynolds and then calculating the friction factor. Okay, so that gives you P out and that gives you P in. And you have the IPR of giving you Q or the IPR giving you PWF. Okay, so that's all you can find in single phase and emulsion. Okay. So I have to go, remember, let's make here a summary. So we go from PR to PWF with the IPR. We go from PWF to P suction with the single phase. Okay, single phase. But we use here with the density of the mixture and the viscosity of the mixture. And then we have to go from the other side, okay, from the wellhead. That wellhead pressure is fixed, is 7 bar, I think. 7 bar. So then you move from there all the way to the discharge of the pump, from P wellhead to P discharge or exit of the pump. And for that you also use the same equation, the same single phase equation, but with, again, with density of the mixture and viscosity of the mixture, which will be the same. Okay, the fraction doesn't change along the tubing, so after I calculate for this segment, I can use it for the other. So that's why I have it here on the table. You have water cut, you calculate these two, okay, and then you use that to go further to calculate. You have bottom hole pressure, go to suction pressure, and then you move from wellhead pressure all the way to discharge. Okay, so let me take a copy of that. Now, what do we have to be careful with the pump? Okay, just to see if the pump will work or not. Okay, so that's what we call method 1. And that is equilibrium removing the ESP. Okay, so from there we go from bottom hole pressure all the way to suction. We stop there. Sorry, reservoir pressure to bottom hole pressure to suction pressure, and then we go from wellhead pressure all the way to discharge pressure, and then we calculate. Okay. What things do we have to verify for pump operation? How to know if the pump works? Okay. What things do we have to make sure?
That the discharge pressure is larger than the inlet pressure?
That, yeah, first that P discharge should be greater than P suction. Okay, that's very correct. Then also we have to make sure that P suction has to be above or equal to the P at the bubble point. Remember, we are not letting the gas go any place. We have a plug. Okay, we have the annulus is plugged. Okay, the fluid simply doesn't have anywhere to go, only than to go through the pump. And pump don't like to handle gas. Okay, only is going to use liquid. So the pressure here should be above the bubble pressure. What else? Okay, the other thing that we have is the envelope. Okay, the operational point should fall on the operational envelope of the pump. Okay, that you remember how it is. It's okay, remember delta P versus Q, that has to be local, and we have these lines, okay, and they are given by maximum frequency, minimum frequency, that is up thrust, and that is down thrust. Okay, so your point has to fall inside. So these are all the things that we have to check. This and the last point, well, the last point is basically the power that I need. Okay, the power required should be less or equal than the total power of the motor. Okay, we're using to move that pump and motor, and we have to make sure that what we need is actually what we have or below. Okay, so those are, in a very simple way, those are all the constraints we have to check. Suction pressure, delta P should be positive, should fall inside the operational envelope, and the power should be less than the power of the motor. The power we estimate by doing delta P times Q divided by, they have to be in consistent units, okay? In consistent units. Divided by the hydraulic efficiency of the pump and the mechanical efficiency of the pump. Okay? This simply, that's the energy that goes to that fluid. Okay? The energy, simply I say the fluid is receiving delta P times Q. But due to the friction, due to all the other losses I have in the pump, I have to give more, which is the hydraulic efficiency. And the mechanical efficiency is the friction in all the axes. Okay? The axis, the motor, etc. Simply the how to say the dry friction between the surfaces. Okay, for that we have, so let's see, these one are really straightforward, right, to check. But now how do we check this one and this one? So you have I have provided for you the map of the pump, okay, in terms of the head. So let me just copy that. So in principle, you have simply to paste to plot your points on that map. Okay, is the point of delta P and Q that you find. Okay, you find from your equilibrium, you find delta P and Q, right, of liquid, and then you simply calculate delta H by taking delta P divided by density. Okay, and simply you plot your point, and your point falls inside the map, and the map is given by, you see here, that's the curve for water, this curve here, and that's the curve when you have viscosity. Okay, some viscosity is reduced, and also that's again the same thing for maximum frequency, medium frequency 45, and lower frequency 30. Okay, so if you're looking at this viscous fluid, the operational map will be this one. Okay, okay, all of this area. Okay, but remember, it's going to change depending on the viscosity that you have. Okay, so the viscosity every year is going to be different. Okay, the map changes or depends on viscosity. On viscosity. Okay, so that map is based on I have made already for you here. It's taking data from here. So you have to substitute the viscosity and the density of your year on those places here to get the new map. Okay, for example, you want to try now for water. Okay, and water is 1000, okay, or 1024, and you go back here. Okay, and it's corrected. Now your new area will be something like that. Okay, if you want to know, I don't want to tell you exactly. Or maybe I can tell you, let's see. I made a correction for those of you who are interested. It's not here. Yep, I use a method to correct the performance of the pump. Okay, but you have to make sure that it falls on that part. But be careful, you have to change according to each year the density and the viscosity. Here you have that curve. You have to have the base performance for water to make the correction. Okay, so that's why I have here another sheet for water, and that's simply the solid points that are here are plotted again here. And now the last part is the power. Okay, and for the power, you have one equation just to make again your life simple. Here you have the pump efficiency, and here you have, where do we have the power? That's very strange, we don't have the power. Yeah, but you can use that equation we have here. Assume a mechanical efficiency 1. Okay, assume mechanical efficiency 1. You have to be in consistent units, so probably you have to change the delta P in pascals and the Q in cubic meter per second. And the efficiency, you're going to use that expression that I showed here. The efficiency of the pump is someplace here. Okay? And let's clarify a bit, what does it have inside? Okay, it has a lot of arguments, so that can be confusing a bit. So function for a hydraulic efficiency. Okay, Q, that's simply the Q of liquid. Okay, F is the frequency, and that frequency, how do I estimate the frequency of the pump? if I come and my point ends up here? I can simply make an interpolation, okay? If this is 45 and that is 60, then it will be someplace in between. Okay, so that will be the frequency that I use. Frequency, in our case, from interpolation. Okay. Reference frequency, I think we have it here someplace. Reference frequency should be here someplace.
It's set on that sheet, just up.
Here?
Doesn't say reference
Yeah,
frequency.
the reference frequency is 60. Okay. You also need, what else do you need? So that is 60. N is the number of stages you have in the pump. Okay. Why? Because usually the curve, that's something we didn't mention before. The curve of the pump, remember, it has a lot of stages. Okay. 1 stage, 2 stage, 3 stage. So the way I build the curve of the pump is that I measure for one single stage. Okay, and then I simply multiply by the number of stages that I have. So if I have 2, if I have 3, okay, this will be the base, okay, delta P of 1 times 2, delta P of 1 times 3, and so forth. Okay, but that number is given here. I think we are using is a pump with 78 stages. Okay, 78 small pumps, one on top of the other. So that's why it takes a few 100 meters. So that's 78 and 78. Then density, viscosity, you have to be careful, use the one for that year. That's the Q of the best efficiency point at the reference frequency. So the line of the best efficiency point, it's is this one, okay, the black one. So it will be that rate here, and that rate is given here, okay, 1987. Okay. And then the rest are, we are basically using a polynomial, okay? And I think I may have it here someplace. Okay? The curve, I'm basically approximating those points are the points measured in the lab, and then I'm approximating that by a polynomial. Okay? And the polynomial, the equation, that's the equation. So these A1, A2, and A3 are basically the coefficients of the polynomial to describe, if I change the rate, how much, what is the delta P I get? Okay? And I have another approximation, another polynomial for the efficiency, this hydraulic efficiency. Okay? So those are all the polynomials you have. I think A1 is for the head, and then B or C is for the efficiency. Okay. And that's it. So simple as that. As simple as that. Okay? But keep these points in mind. Okay? Delta P should be, pressure at the suction should be smaller than pressure at the discharge. The suction should be greater than the bubble point pressure. The point should fall inside. And you don't have to see how I made the correction. Okay? Simply you have to use that plot and then change. You have to change the input. Okay, the only input you have to change are these two, viscosity and density, to get the new map.
You have to check each year?
Each year, yeah. Each year will have a different map. Okay.
So will you do this manually, or?
You have, that's for you to find out. How are you going to do it? Okay. You don't have too many years. Okay, so if you want to do it brute force, you are 3, so each one of you takes a year, and okay. But you can do some more fancy solution. Okay, and the most tricky part is the power. Okay, which the equation is very simple, but the equation for the hydraulic efficiency is not so simple. Okay, because we have to correct for viscosity. Higher viscosity creates higher loss, creates lower efficiency. So for that we use this ugly expression with a lot of input, but now you know where to find that input. Okay, the coefficients, I think they are someplace here. Okay, you have A, and you have the coefficients for the viscosity, for the efficiency, where they are for the efficiency. And maybe that's an old version. That's a bit strange. I don't know why it doesn't have the power or the efficiency. But basically you have to use these exponents. Okay? Okay? Clear? Easy peasy? Yeah.
When is the exercise going to be delivered?
I think maybe in 2 weeks from now.
Okay.
Okay? Or unless you want to have it sooner. So.
No, it's fine.
That's fine? Okay. Okay, but that's the thing you have to check for pump. Yeah, what else we had on the list today? Any question before we continue? You have to start doing it, okay? I explained to you how I do it, the equations, what you have to take into account, but you learn only by doing, okay? So you have to go yourself and try to understand how if the things make sense, okay? And things might not always make sense. Should we go now a bit on compression? Yeah? Yes? Okay. I'm surprised. I don't have, I'm a bit tired, but you want to keep going, so that's fine. Okay, so let's now talk about compression, okay? They were not enough? Who doesn't have a chart? Okay. Yeah. Can you just partner up, just pass it, if you can group 2 and 2 and pass it. I will bring more tomorrow. Okay. Okay, you remember when we have a compression we speak about gas, okay? Usually pure gas. And we take a pressure 1, temperature 1, and at the end we obtain pressure 2 and temperature 2. Okay, we give energy to the fluid by increasing pressure, but we also get the undesired effect because the fluid is compressible that the temperature is also going to change. Okay, usually it's going to increase. So you learned from one of your courses previously that we can make energy balance on this control volume, right? We have to go a bit into the a bit into the fundamentals. Mass flow, and we have here, what was it? Energy entering into the control volume minus energy leaving the control volume. Okay, and that energy, how do we express it? That energy has a few so I have kinetic energy, then I have elevation, then I have, what else do I have? I have this H, enthalpy. Okay, you take all the energy of the fluid coming in, that you basically have internal energy, you have pressure, you have kinetic energy, and you have potential energy. Okay, then we can say that these are the velocities, the change in kinetic energy, the change in elevation for a compressor is basically zero. We can neglect it. Okay, and we have basically the purpose of the compressor is not to exchange energy with anyone. It's just to give power. Okay, so we can say that one ideally should be zero. So we end up with the equation mH1 minus H2. Okay, and here remember we have the convention that if the power is entering into the system, yeah, ringing a bell from
No, I just.
Is it H2 minus H1?
H,
Because
yeah, because okay, that is correct. So then we made a mistake, okay, or I made a mistake.
I was just laughing at the letters. Sorry. I didn't understand them.
Okay, that's okay. So this power is the energy of 2 is usually bigger than the energy of 1 because I'm adding energy to the stream. Okay, therefore that product is that difference is negative, and that value is negative because I'm introducing heat. I'm introducing work. Okay, to that volume. So it looks, at least it makes sense. Okay, so now what is the most efficient way to go from 1 to 2? Let's say in our case that we have, it was the case of a template for our exercise, right? We were doing. Where is it? Okay, for these two, yeah, this Gullfax, okay, for our Gullfax case, for the Gullfax exercise. Okay. You remember what kind of pressures do we have to change from what value to what value? What were the conditions at the inlet of the compressor? You remember? Or you haven't done the exercise yet? Okay, so let's say maybe, you know, pressure will be 50 bar and the temperature at the suction is 20 degrees Celsius. Okay, and then let's say at the outlet it will be, I want to go up to 100 bar. That's the goal. That's the pressure I need required to flow through the line. Okay, I'm not sure about the numbers. They are going to be different. They probably are different. Okay, so we go to our chart. For that we have the chart of, we are going to assume is very close to methane, this fluid. Okay, and let's locate first the inlet on that diagram. Okay, that's methane. We are saying our gas is very close to methane, and we can use this diagram, and here we can see a lot of interesting things. Okay, but we first look, you have to be careful. These lines that are going like that, okay, these are isentropic lines. Okay, these are isentropy lines. The lines that are going on this direction, these are isotemperature lines. We use another color. Isotemperature lines. Isothermal. Okay, that is isothermal. And then on the x-axis we have the enthalpy. That you see now, that's something I need. The enthalpy tells me how much work, how much power I need to put into that fluid. Okay, and pressure is basically the change I want to make in pressure. Okay, So we have at the suction we have 50 bar. How much is 50 bar to megapascals? How much is that? Simply 5, right? So that will be 2, 3, 4, 5. So that's the line for 50 bar. And the inlet temperature was 20. Okay, so here we have that will be 0 here, 10, 20, 30, 40, and 50. Okay, so 20 is that line, and that will be my point. That's the inlet to the compressor. Okay, that point here. You have to see it, maybe it's not so clear from the screen. Okay, where do I want to go? To which pressure I want to take that fluid to? Okay, I want to take it to 100 bar. Okay, I want to take it to 10 megapascals. So P at the discharge is 100 bar or 10 megapascals, and I want to take it, it will be basically that line. Okay, so I want to make it someplace there, but you see the temperature can change very much. Okay, I can go like this, I can go like that, I can go like that. I have to go somehow. The most efficient way that I use all the energy, the best way, the most efficiency way, is simply make it isentropic. It means there are no losses, no irreversibilities. I make the ideal, perfect process to compress that gas. So what is the isentropic path on this chart? Is basically, remember we have these isoentropy lines. That's why this chart is so powerful. So we come here and we find that point. Ideally, if I have no losses, I use all the power just to compress the fluid, I will reach to that point, number 2. Okay, what temperature do I get on that point?
70.
Around, this is 100, I think, right? And this is 90. Yeah. So it will be maybe 98, something like that. Okay, I have to go from 150 bar to 100 bar, and I move isentropically. Okay, that's the best way or the most efficient way to do it. And I find, temperature 2, it's around 98 or no, sorry, it's 87. Okay, or 88. Let's see one more. This line here is 100, this one is 90, and this one is 80. Okay, so we have it between 80 and 90. So let's say 80, 85 or 80 something. All other processes, and what is the work that I need to make that compression? Okay, remember the work was, if I'm going to put it without the sign, is H2 minus H1, and that will be isentropic, ideally. Okay, so what is the difference in enthalpy between these two? 100. Okay, H2S, 100 kilojoule per kilogram, minus H1, how much was that? 0, 100, so like 25. Okay, what is the mass flow that I have? How much was this field producing in plateau rate? Was 10 million, right? So the Q of the field was 10 million standard cubic meter per day. How much is that in mass flow? I don't have the number, but I think the density of the gas at standard conditions was something like 0.68. Okay, and then you can find that the mass flow of gas is 10 times 0.68, and you want to convert it to the right units. Okay, so we have to divide by that gives you we should close at 10. Okay, 78 kilogram per second. Okay, a huge amount of gas, that is. Okay, 78 kilogram per second. 78 kilogram per second. And how much is that? Well, how much energy do we need at the end? That will be 75 times 5,902 kilojoule per second. Okay, and that is how much? How much is a joule per second? That is 5.9 megawatts. Okay, that's how much ideally, if I manage to make it ideally, how much big of a motor I need to move that compressor. Okay, a compressor of 5.9 megawatt. Okay, so let's close it now, not do anything else, but that's the best case. Okay, next time we're going to look at what is the real case, how the curve looks like, and you can think that the fluid will come warmer. Okay, basically because I'm going to lose energy warming up that fluid. So we're going to try to predict how that temperature, how much is that temperature, because we're going to see that is important for something we have to take into account for the operation of the compressor. Okay? Yes, any question before we close? No? Okay, see you tomorrow.